Picture a telescope in the Chilean desert, its lens trained on a patch of sky that looks empty to the naked eye. The night is clear, the air is thin, and the Milky Way stretches overhead like a river of light. 4 exposures click in succession, each capturing photons that have traveled across unimaginable distances. In the data, buried among millions of stars and galaxies, there's a dot. Magnitude 17.8, barely brighter than the background noise of the universe itself. The automated software flags it immediately, not because of what it is, but because of what it's doing. It's moving. Moving fast. Moving wrong. This is how discovery happens in the 21st century. Not through a lone astronomer peering through an eyepiece, but through algorithms scanning terabytes of data, looking for patterns that shouldn't exist. The Asteroid Terrestrial Impact Last Alert System, ATLAS for short, was designed for this kind of work. 4 robotic eyes scattered across the planet, constantly scanning for rocks that might pose a threat to Earth. The Chilean station at El Sase Observatory had just captured something that would challenge everything we thought we understood about visitors from beyond our solar system. Within hours, the alert ripples through the global astronomical community. Observatories on multiple continents swing their instruments toward these coordinates. What begins as a routine near-Earth object check, the kind performed hundreds of times per year, transforms into something far more significant. Initial calculations suggested this might be another asteroid on a potentially hazardous trajectory. But as more observations came in, as more positions were measured and trajectories calculated, the mathematics told a different story. The trajectory is hyperbolic, which means this visitor came from somewhere else, from the space between stars. And after its brief passage through our neighborhood, it will return to that darkness forever. The concept of hyperbolic trajectories is fundamental to understanding what makes this object special. Most objects in our solar system follow elliptical orbits, closed loops that repeat endlessly. Their orbital eccentricity, a measure of how stretched out the ellipse is, ranges from 0 for perfect circles to just under 1 for highly elongated ellipses. But when eccentricity exceeds 1, the orbit opens up into a hyperbola. The object approaches from infinity, swings around the Sun once, and departs toward infinity. It's a one-time visit, never to be repeated. They call it 3I Atlas, the third confirmed interstellar object in human history. The I designation stands for interstellar, a category that didn't exist until recently. The first was Oumuamua in 2017, that mysterious elongated shape that accelerated without visible propulsion, defying easy explanation and launching 1,000 debates about its nature. The second was Borisov in 2019, discovered by an amateur astronomer using equipment he built himself. Borisov behaved more like a conventional comet, but carried its own chemical mysteries that hinted at formation conditions different from our solar system. Now we have number 3. And from the very first observations, it's clear that 3I Atlas is neither a repeat of what came before, nor something entirely comfortable within our frameworks of understanding. It occupies a middle ground between the exotic strangeness of Oumuamua and the reassuring conventionality of Borisov. It has characteristics of both, which makes it perhaps the most intriguing of the 3. The discovery wasn't quite as sudden as it appeared. When astronomers knew where to look, they found ghosts in archived data. The Zwicky Transient Facility at Palomar Observatory had captured it multiple times without recognizing what they were seeing. Atlas stations in South Africa and Hawaii had recorded it passing through their fields of view. The Chilean station had images dating back weeks. It had been there all along, drifting through frames, a needle in a haystack of millions of stars and galaxies, waiting for pattern recognition software to notice its peculiar motion. This retroactive discovery phenomenon is common in modern astronomy. Our surveys capture so much data that detailed analysis lags behind acquisition. Objects can appear in images weeks or months before anyone notices them. Going back through archives to find pre-discovery observations is standard practice now. It allows astronomers to extend the observational baseline, improving orbital calculations, and giving more time to study objects that might otherwise slip away unnoticed. In the case of 3I Atlas, pre-discovery observations extended back to mid-May, almost 2 months before official discovery. This meant the comet had been active and visible for an extended period, slowly approaching the inner solar system while our instruments recorded its progress without understanding its significance. Those early images would prove crucial for understanding the comet's activity levels and how they changed with distance from the Sun. 2 days after discovery, the European Southern Observatory's Very Large Telescope locked onto the target. The name Very Large Telescope sounds almost comically straightforward, but it's an accurate description. 4 massive mirrors, each over 8 meters across, working together in Chile's Atacama Desert, the driest place on Earth where atmospheric interference barely exists. At an altitude of 2,635 meters, above much of the water vapor that distorts astronomical observations, the VLT represents one of the most powerful ground-based observatories ever constructed. Over 13 minutes on a clear night, the VLT captured multiple exposures showing the comet's movement as a dotted line across background stars. Each dot represents a snapshot in time, breadcrumbs marking the visitor's path across the celestial sphere. This technique of tracking moving objects against fixed star backgrounds is ancient, dating back to the earliest telescopic observations. But modern CCDs can capture motion with precision that would have seemed impossible just decades ago. The close-up images revealed early structure, not just a point of light anymore, but something with dimension and complexity. A fuzzy glow surrounding a brighter core, the unmistakable signature of an active comet. The Coma was already forming, which was unexpected and immediately intriguing. The comet was still beyond Jupiter's orbit, more than 4 astronomical units from the Sun. At that distance, sunlight should be too weak to trigger significant activity in most comets. To understand why this matters, we need to understand how comets work. They're essentially dirty snowballs, mixtures of ice and rock that spent most of their existence in the cold outer reaches of planetary systems. The ices are primarily water, but also include more volatile substances like carbon monoxide, carbon dioxide, methane, and ammonia. Each of these substances has a different sublimation temperature, the point at which solid ice transforms directly to gas without passing through a liquid phase. Water ice, the dominant component in most solar system comets, doesn't sublimate significantly until the comet gets relatively close to the Sun, typically inside about 3 astronomical units. That's roughly the distance of the asteroid belt. But 3I Atlas was showing activity at more than 4 astronomical units, well beyond where water sublimation should be driving significant outgassing. This immediately suggested something about the comet's composition. It contained volatile materials, chemicals that evaporate easily even in the weak sunlight of the outer solar system. Carbon monoxide, perhaps, which sublimation at temperatures found beyond Jupiter's orbit. Or carbon dioxide, which lies between water and carbon monoxide in volatility. Or maybe something else entirely. Something we don't routinely see in solar system comets. The question of what exactly was vaporizing became urgent, and answering it required spectroscopy. The Gemini North Telescope in Hawaii brought spectroscopic instruments to bear. Sitting at nearly 14,000 feet elevation on Mauna Kea, above 40% of Earth's atmosphere, Gemini occupies one of the premier observing sites on the planet. The summit of Mauna Kea hosts a collection of telescopes that represent billions of dollars of investment in astronomical infrastructure. All there because the observing conditions are extraordinary. Spectroscopy is the art and science of splitting light into its component wavelengths. When white light passes through a prism or diffraction grating, it spreads into a rainbow. But that rainbow isn't smooth. It's crossed by dark and bright lines, the fingerprints of chemical elements. Every atom and molecule absorbs and emits light at specific wavelengths determined by quantum mechanics. By analyzing which wavelengths are present and which are missing, we can determine what substances are present in distant objects. The Gemini observation showed a comet with an unusually large coma for its distance from the Sun. The fuzzy cloud extended tens of thousands of kilometers from the nucleus, far larger than expected for such a distant, presumably small object. But what really caught attention was what came later, when more detailed analysis revealed chemical signatures that didn't quite match typical expectations. Not alarming, not impossible, just interesting. The kind of discrepancy that makes scientists lean forward in their chairs and request more telescope time. The kind of detail that suggests the object might have a story to tell about where it came from and how it formed. This is the moment when curiosity transforms into focused investigation, when an interesting object becomes a research priority. Then Hubble entered the picture. The Hubble Space Telescope, launched in 1990 and still operating decades later, remains one of humanity's most productive scientific instruments. Orbiting above Earth's atmosphere, it has access to wavelengths that ground-based telescopes can't observe, and can achieve angular resolution limited only by the laws of physics, rather than atmospheric turbulence. In late July, Hubble turned its attention to 3I Atlas. The comet was 277 million miles from Earth at the time, approaching the inner solar system but still far outside Mars' orbit. At that distance, even Hubble's remarkable capabilities were challenged, but the observations succeeded, producing what remains the sharpest image ever obtained of this object. In the picture, the comet appears as a teardrop-shaped cocoon of dust and gas glowing against the black of space. Background stars are streaked into lines because Hubble was tracking the comet's motion, keeping it centered in the frame while everything else blurred past. This differential motion technique is standard for observing solar system objects, but it creates striking images where the target appears frozen while the universe streams by. The teardrop shape itself wasn't unusual. Comets often develop asymmetric comas as they warm up, as outgassing rates vary across the nucleus surface, due to differences in composition, temperature, and solar illumination. But the direction of the elongation caught immediate attention. The dust cocoon extended toward the Sun, not away from it. Every comet develops a tail that points away from the Sun. This is one of the most fundamental and easily observed behaviors in cometary science. Solar radiation pressure, the physical push of sunlight on dust particles, drives dust away from the nucleus. The solar wind, a stream of charged particles flowing outward from the Sun, pushes ionized gas away. Both forces act radially outward from the Sun, creating tails that stream away regardless of the comet's direction of motion. Their tails are like wind-blown hair, always streaming away from the solar wind source. Except 3I Atlas had something pointing the wrong direction. An antitail. A sunward extension that seemed to defy basic physics. Initial speculation suggested it might be an optical illusion, a projection effect caused by viewing angle. Sometimes dust trails can appear to point toward the Sun if you're looking at them from the right perspective, even though they're actually pointing away in three-dimensional space. This happens when we view the orbital plane of a comet nearly edge-on. Dust particles ejected from the nucleus spread out along the comet's orbital path, both ahead and behind. If we're looking at this distribution from a shallow angle, the particles ahead of the comet can appear to be pointing toward the Sun, even though they're actually following the comet's orbit. It's a geometric effect, well understood, and commonly observed in bright comets. But detailed analysis of the Hubble image showed this wasn't simple geometry. The extension was real, a genuine jet, or outflow of material directed toward the Sun. The 2-to-1 elongation ratio observed in the sky corresponded to roughly 10-to-1 elongation in three-dimensional space, after accounting for viewing angle. Something about 3I Atlas was creating a jet of material that pointed toward the Sun, and nobody had a comfortable explanation yet. The Hubble observations also allowed astronomers to constrain the nucleus size, though with frustrating uncertainty. By measuring total brightness and estimating surface reflectivity, they calculated the solid core couldn't be smaller than 440 meters and couldn't be larger than 5.6 kilometers in diameter. That's an enormous range, spanning more than an order of magnitude in linear dimension and several orders of magnitude in mass. The uncertainty stems from a fundamental problem in observing active comets. The nucleus is surrounded by a coma of dust and gas that contributes to the total brightness. Without knowing exactly how bright the coma is, we can't determine how much light comes from the nucleus itself. If the coma is very bright, the nucleus must be small and faint. If the coma is relatively dim, the nucleus must be larger and brighter. Observational constraints can narrow the range, but not eliminate the ambiguity. What the observations did tell us with confidence is that 3I Atlas was substantially bigger than Oumuamua, which had been maybe a few hundred meters across at most. If Atlas sat at the larger end of the size estimate, approaching 5 or 6 kilometers in diameter, it could be 1,000,000 times more massive than the first interstellar visitor. That kind of size difference wasn't just notable, it was statistically peculiar. Detection biases strongly favor finding large objects over small ones. Larger objects reflect more light and are visible from greater distances. Small objects can pass through the inner solar system completely undetected, unless they happen to pass very close to Earth or have unusually high reflectivity. So we expect our sample of detected interstellar objects to be biased toward the large end of the size distribution. Yet here we were, only 3 interstellar objects discovered, and the third was potentially the largest. If 3I Atlas really is several kilometers across, it would be an extraordinary find, a rare large specimen that could tell us about the formation and ejection of planetary system debris on scales we hadn't accessed before. But the size remained uncertain, and resolving that uncertainty became a priority. The James Webb Space Telescope observed 3I Atlas with its near-infrared spectrograph. Webb, launched at the end of 2021 and positioned at the second Lagrange point beyond the Moon's orbit, represents the cutting edge of infrared astronomy. Its primary mirror, 6.5 meters across and composed of gold-coated beryllium segments, collects infrared light with unprecedented sensitivity. Infrared observations are crucial for cometary science because many molecular vibrations and rotations occur at infrared wavelengths. Water, carbon dioxide, carbon monoxide, methane, ammonia, all the volatiles we expect in comets have characteristic infrared signatures. Webb can detect these signatures with precision that ground-based telescopes struggle to match, partly because Earth's atmosphere is opaque at many infrared wavelengths. Webb sees in wavelengths invisible to human eyes, heat signatures and molecular vibrations that reveal chemical composition with stunning precision. The near-infrared spectrograph captured spectral data across a range from 0.6 to 5.3 micrometers, building up a detailed chemical inventory of the gases surrounding the nucleus. Each wavelength range targets different molecules, and combining them provides a comprehensive composition measurement. What Webb found was unprecedented and immediately generated excitement across the planetary science community. The coma around 3I Atlas was dominated by carbon dioxide, not water. Carbon dioxide. This single result challenged assumptions about interstellar comet composition and raised fundamental questions about where and how this object formed. In most comets from our solar system, water ice makes up the bulk of volatile material. Typical comets are roughly 80% water ice by volatile content, with carbon monoxide, carbon dioxide, methane, and other compounds making up the remainder. When they warm up near the sun, they release water vapor as their primary gas, along with smaller amounts of these other compounds. This composition reflects formation conditions in our solar system's protoplanetary disk, where water ice was abundant and stable. But 3I Atlas was releasing 87% carbon dioxide by mass, only 9% carbon monoxide, and just 4% water. 4%! That ratio is 16 times more extreme than what you'd expect for a typical comet at the same distance from the sun. Some solar system comets have slightly elevated carbon dioxide levels, particularly those originating in the outer solar system, where carbon dioxide ice is more stable. But nothing like this. Nothing even close. 3I Atlas was behaving as if it formed in a completely different kind of environment, under conditions unlike anything we see in our solar system's comet populations. The implications were profound. Either the comet formed close to a carbon dioxide ice line in its home star's protoplanetary disk, in a region where carbon dioxide condensed preferentially over water, or it experienced processing over billions of years that altered its surface chemistry. Radiation processing is a known phenomenon. Cosmic rays and ultraviolet starlight can break chemical bonds and create new compounds on comet surfaces. Over millions or billions of years in interstellar space, this processing could, in principle, alter surface composition. But transforming a water-rich comet into a carbon dioxide-rich one would require extreme processing, far more than theoretical models typically predict. The more likely explanation is that 3I Atlas formed in a carbon dioxide-rich environment. Different stars have different metallicities, different carbon to oxygen ratios, different temperature structures in their protoplanetary disks. A system with high carbon to oxygen ratio might produce comets with elevated carbon dioxide relative to water. A disk with unusual temperature gradients might have carbon dioxide ice dominating in certain regions. This single composition measurement told us that planetary systems around other stars can be fundamentally different from ours, producing objects with chemical compositions we don't see locally. It's direct evidence of diversity in planet formation, delivered to us by an interstellar visitor that carried samples of its home system across light years of space. The Webb data also showed enhanced outgassing specifically in the direction toward the Sun, confirming that the antitail feature was real and active. Mass loss rates calculated from the spectrum indicated the comet was shedding 129 kilograms of carbon dioxide per second, 6.6 kilograms of water per second, and 14 kilograms of carbon monoxide per second. Total mass loss about 150 kilograms every second. That sounds like a lot, until you realize the nucleus potentially weighs tens of billions of tons. Let's do the math. A spherical nucleus 5 kilometers in diameter with density of 500 kilograms per cubic meter would weigh about 33 billion kilograms. At a mass loss rate of 150 kilograms per second, it would take over 2,000 days to lose just 1% of its mass. The comet could keep outgassing for years without losing a significant fraction of its total mass. During its passage through the inner solar system, from discovery in July through closest approach in late October, 3I Atlas would lose approximately 2 million tons of material. That sounds enormous, but it represents less than 0.01% of the nucleus mass. It's barely scratched, just a surface layer, averaging a few centimeters thick across a multi-kilometer object. The comet has reserves, and whatever chemistry is driving this unusual composition, it's not going to run out anytime soon. NASA's SPHEREx spacecraft captured 3I Atlas in near-infrared wavelengths during a week-long observation campaign in mid-August. SPHEREx is a relatively new mission, designed to map the entire sky, looking for water ice and organic molecules. Its acronym stands for Spectrophotometer for the History of the Universe, Epoch of Reionization, and ICE's Explorer, which gives you a sense of its broad scientific objectives. When SPHEREx turned toward 3I Atlas, it detected an extended carbon dioxide plume stretching out to at least 348,000 kilometers from the nucleus. That's almost the distance from Earth to the Moon. Think about that scale for a moment. The carbon dioxide cloud was enormous, far larger than anything visible in optical wavelengths, where dust scattering dominates the appearance. This extended carbon dioxide envelope revealed something important about how gas expands from comets. When molecules sublimate from the nucleus surface, they're moving at thermal velocities determined by temperature and molecular mass. Carbon dioxide molecules at typical cometary temperatures move at roughly 400 meters per second. As they expand outward, they collide with each other at first, but eventually the density drops low enough that collisions cease and molecules fly freely into space. The extent of the carbon dioxide cloud depends on production rate, expansion velocity, solar radiation that can break apart molecules through photodissociation, and the solar wind that can ionize and sweep away neutral gas. The fact that SPHEREx detected carbon dioxide out to 348,000 kilometers meant production rates were high, molecular lifetimes were long, or both. SPHEREx also helped constrain nucleus size by measuring scattered sunlight at 1 micrometer wavelength, right at the boundary between visible and near infrared. If the dust plume made only a small contribution to total brightness at that wavelength, the nucleus diameter could be as large as 46 kilometers for very low reflectivity surfaces. If true, that would make 3I Atlas truly massive, more like a small icy moon than a typical comet. But that estimate came with significant uncertainties. Reflectivity was unknown and could vary by factors of several. Dust contribution to brightness was uncertain. The 46-kilometer estimate represented an extreme upper bound rather than a likely value. Most astronomers considered it improbable, suspecting the nucleus was probably at the smaller end of the possible range, maybe 1 or 2 kilometers across. The uncertainties remained frustratingly large, but each observation narrowed the possibilities. Combining Hubble's visible light measurements with Webb's infrared spectroscopy and SPHEREx's near-infrared photometry provided multiple constraints that, taken together, painted a more complete picture than any single observation could provide. The Keck Observatory in Hawaii brought its cosmic Webb imager to the target in late August. Keck consists of twin 10-meter telescopes, among the largest optical/infrared telescopes in the world. The Cosmic Webb Imager is an integral field spectrograph, a sophisticated instrument that captures spectra across a two-dimensional field of view, effectively producing a 3D data cube with 2 spatial dimensions and 1 spectral dimension. The resulting images showed the Coma structure in beautiful detail and confirmed the continued presence of the anti-tail feature pointing toward the Sun. But the real surprise came from the spectroscopic data, which revealed chemical signatures nobody expected. Keck detected prominent emission from nickel atoms in the gas around 3I Atlas. Nickel. Not particularly weird by itself, since nickel is a common element in rocky and metallic materials throughout the universe. Small amounts of metallic atoms show up in some comet spectra, released when dust particles are vaporized by solar radiation, or when subsurface materials are exposed to vacuum and sunlight. Iron and nickel are among the most commonly detected metals in comet spectra because they're abundant in cosmic materials and have strong spectral lines in visible and ultraviolet wavelengths. Except Keck also looked specifically for iron emission and found nothing. No iron lines at all, or at least none strong enough to detect above the noise. This was strange. Every other comet ever studied, including the previous interstellar comet Borisov, shows iron and nickel together when they show up at all. The two metals are chemically similar, have nearly identical cosmic abundances, and almost always occur together in natural materials. But 3I Atlas had nickel without iron, a ratio orders of magnitude different from anything seen before. The nickel emission extended to about 600 kilometers from the nucleus, while cyanide, also detected in the same observations, spread to roughly 840 kilometers. The nickel was more centrally concentrated, suggesting it was coming directly from the nucleus surface, rather than being produced by chemical reactions in the outer coma. Mass loss rates for these trace species were tiny compared to carbon dioxide. The comet was releasing about 0.9 grams per second of nickel and 3.9 grams per second of cyanide. These are barely measurable amounts, roughly equivalent to a few drops of water per second. But their presence and unusual ratios added to the growing sense that 3I Atlas was not following the usual script. Here's why the nickel without iron matters so much. On Earth, nickel without iron occurs primarily in industrial processes, where nickel is refined from ore using a technique involving nickel tetracarbonyl. This is a compound where a single nickel atom binds to 4 carbon monoxide molecules, forming NiCO4. The process happens at specific temperatures and pressures, and is used in the Mond process to create ultra-pure nickel for industrial applications. Nickel tetracarbonyl forms when nickel metal reacts with carbon monoxide at elevated temperatures. It's volatile, subliming at relatively low temperatures, which allows nickel to be separated from other metals that don't form similar compounds. The process is elegant and efficient, but it's also industrial. Nobody expected to see something resembling industrial chemistry happening spontaneously in a comet from another star system. Yet the spectral data suggested exactly that kind of process might be occurring. Some mechanism in or on 3I Atlas was creating conditions where nickel could be released selectively without iron tagging along. Whether that meant exotic surface chemistry involving carbon monoxide, unusual nucleus composition with nickel-rich minerals that lack iron, or something else entirely, nobody knew for certain. It was just deeply, fascinatingly weird. The observations also provided critical data on dust particle sizes and composition based on how light scattered off them at different wavelengths. This technique, called polarimetry, measures the polarization state of scattered light. Different particle sizes, shapes, and compositions produce different polarization signatures, allowing astronomers to infer properties of dust they can't directly image. The dust in 3I Atlas's Coma showed extreme negative polarization at small phase angles. This is technical language for a specific optical phenomenon where light scattered at certain angles has its electric field oriented preferentially along one direction. The degree of polarization provides information about particle size distribution and composition. The extreme negative polarization suggested dust particles with unusual properties, possibly a mixture of icy and dark carbonaceous material, similar to what's seen in trans-Neptunian objects in our own solar system. This finding hinted that 3I Atlas might have formed in the cold outer regions of its home planetary system, where materials similar to Kuiper Belt objects dominate. But despite these exotic spectral signatures, the bulk dust and ice properties appeared broadly similar to solar system comets. The dust particles were roughly the right size, the ice-to-dust ratio seemed reasonable, and the way dust scattered light followed familiar patterns. This was a reminder that 3I Atlas, despite its chemical strangeness, was still fundamentally a comet. A mixture of ice, rock, and dust following basic rules of cometary physics. Just a comet that had seen different formation conditions than the ones we're used to studying. Throughout August, ground-based telescopes continued their campaign to characterize 3I Atlas. The observations provided data on the dust particle sizes and composition based on how light scattered off them at different wavelengths. This technique, called polarimetry and photometry combined, measures both the intensity and polarization state of scattered light at multiple wavelengths. Different particle sizes, shapes, and compositions produce different scattering signatures. Small particles, comparable in size to the wavelength of light, scatter more blue light than red through a process called Rayleigh scattering. Larger particles scatter all wavelengths more equally. Very large particles, much bigger than the wavelength of light, scatter light geometrically, following the rules of ray optics. By measuring how brightness varies with wavelength, astronomers can infer the size distribution of dust particles. By measuring polarization, they can learn about particle shape and composition. Spherical particles produce different polarization than irregular ones. Icy particles produce different signatures than rocky ones. It's a powerful diagnostic technique that allows remote sensing of particle properties we could never measure directly. The dust in 3I Atlas's Coma showed color indices consistent with reddish particles containing organic compounds. The BV color was 0.98, VR was 0.71, and the spectral slope was about 16% per 100 nanometers. These numbers mean the comet reflected more light at longer, redder wavelengths than shorter, bluer wavelengths. This reddish coloration is typical of organic-rich materials that have been processed by radiation over long timescales. Many solar system comets show similar colors, particularly those from the Kuiper Belt and Oort cloud that formed in the cold outer reaches of the planetary system. The similarity suggested 3I Atlas formed in a similar cold environment in its home system, accumulating organic compounds that gave it this characteristic color. But despite these exotic spectral signatures in the gas phase, the carbon dioxide dominance, the nickel without iron, the bulk dust properties appeared broadly similar to solar system comets. The particles were roughly the right size, the ice-to-dust ratio seemed reasonable, and the way dust scattered light followed familiar patterns. This was simultaneously reassuring and puzzling. It suggested that while the volatile composition of 3I Atlas was unusual, possibly reflecting different formation conditions or processing history, the solid refractory component was more conventional. The rock and organic matter that made up the dust particles resembled what we see locally. This makes sense if the building blocks of planetary systems, silicate minerals, carbonaceous compounds, water ice, metal grains, are broadly similar across different star systems. The fundamental physics and chemistry of planet formation should be universal. Stars form from collapsing molecular clouds. Those clouds contain heavy elements synthesized in previous generations of stars. As the cloud collapses and a protoplanetary disk forms, temperature and pressure gradients cause different materials to condense at different locations. Close to the star, only refractory materials survive. Further out, ices condense. The details, exact temperatures, exact compositions, exact locations of ice lines, vary depending on the star's mass, luminosity, and the disk's properties. But the overall pattern should be similar, so finding that 3I Atlas's dust resembles solar system comet dust makes sense. The unusual volatile composition, dominated by carbon dioxide rather than water, tells us about specific formation conditions that differ from what's common in our system. The observations also provided critical data about mass loss rates and activity levels. By measuring the brightness of the Coma and knowing something about dust properties, astronomers could estimate how much material the comet was ejecting. The answer was striking. Approximately 0.1 to 1.0 kilograms per second of dust, plus the 150 kilograms per second of gas measured by Webb. Let's put those numbers in context. A kilogram per second might not sound like much, but over the course of a day, that's 86,400 kilograms, or about 86 metric tons. Over the several months from discovery through perihelion, the comet would lose millions of kilograms of material. Yet this represents a tiny fraction of the total nucleus mass, assuming it's several kilometers across. The dust particles were estimated to be moving at velocities between 0.01 and 1.0 meters per second, quite slow compared to typical gas expansion velocities of hundreds of meters per second. This makes sense, because dust particles are much more massive than gas molecules. When gas expands from the nucleus, it can drag dust particles along, but the dust accelerates more slowly because of its higher mass. Small micron-sized particles can be accelerated to velocities approaching the gas velocity because drag forces are strong relative to particle mass. But larger millimeter-sized particles, with much higher mass-to-surface area ratios, accelerate more slowly. The observed velocity range of 0.01 to 1.0 meters per second suggested a mixture of particle sizes, with the larger particles dominating the mass budget. This is important for understanding how comets evolve. If a comet ejects mostly small particles, it loses mass quickly, but the particles disperse rapidly and become undetectable. If it ejects mostly large particles, mass loss is slower, but the particles remain visible longer, creating a more persistent dust tail. 3I Atlas appeared to be ejecting a healthy mixture, creating both a bright coma from small particles and a developing tail from larger ones. The Gemini observations from both North and South telescopes provided additional spectroscopic constraints. Deep, multicolor images through red, green, blue, and ultraviolet filters revealed that 3I Atlas now displayed a distinct tail, a proper dust tail stretching away from the sun as comets are supposed to have. The transformation from anti-tail to regular tail was underway. The tail spanned about 1/12 of the field of view in the Gemini images, roughly several arc minutes on the sky. At the comet's distance, this angular size corresponded to several tens of thousands of kilometers in physical extent. The tail was relatively short compared to some bright comets that develop tails millions of kilometers long, but it was clearly visible and growing. The Gemini South observations were particularly special because they happened as part of the Shadow the Scientist program, a public outreach initiative where citizen scientists could watch live as professional astronomers conducted observations on a world-class telescope. Karen Meach from the University of Hawaii led the scientific program, with Ben Yang guiding interpretation of spectral data and providing expertise on cometary composition. The public got to see real science in action, watching as the team obtained deep images, discussed what they were seeing, adjusted observing strategies in real time, and worked through the challenges of observing a faint, fast-moving target. This kind of direct engagement helps bridge the gap between professional astronomy and public interest, showing that science is a dynamic process of discovery rather than a static collection of facts. Then, scientists found something else buried in the archives, something that would dramatically change the interpretation of 3I Atlas's behavior. The 2-meter twin telescope at Teide Observatory in Spain's Canary Islands had captured the comet on August 2nd, combining 159 exposures of 50 seconds each into a deep composite image. This image wasn't released publicly until mid-October, but when it finally appeared on the Astronomers' Telegram, it showed something remarkable. In the composite, the nucleus appeared as a large central concentration, surrounded by a white glow, representing the Coma. And breaking through that glow, like a wound in the fabric of the cloud, was a sudden fan-shaped feature extending toward the sun. A jet. A massive jet of gas and dust, marked in purple in processed versions of the image, blasting off the nucleus directly toward the sun. Jets are common features on comets, and they've been studied extensively. As the nucleus surface heats unevenly due to rotation, topography, and variations in composition, pockets of gas beneath the crust build up pressure. Eventually, that pressure exceeds the strength of the overlying material, and the gas bursts through weak spots. The resulting jet is a collimated stream of material, often visible for hours or days before the active region rotates out of sunlight, where the activity subsides. The most detailed observations of cometary jets came from the European Space Agency's Rosetta mission, which orbited comet 67P Churyumov-Gerasimenko for 2 years. Rosetta watched jets turn on and off, mapped their locations on the nucleus surface, measured their composition and particle velocity, and tracked how they changed with heliocentric distance and illumination conditions. What Rosetta showed is that jets are complex and variable. Some are powered by water ice sublimation, others by more volatile species, like carbon dioxide or carbon monoxide. Some emanate from smooth plains, others from rough terrain or cliff edges. Some are narrow and focused, others broad and diffuse. The jets respond to surface temperature, which changes with solar illumination, nucleus rotation, and seasonal effects. The jet on 3I Atlas was unusual not because jets are rare, but because of its orientation. It pointed directly toward the sun, contributing to the anti-tail feature that Hubble and other telescopes had been tracking. Most jets spray in various directions, based on surface topography and rotation. But this jet was oriented sunward, suggesting the active region happened to be on the subsolar point, the spot where the sun appears directly overhead from the nucleus surface. Estimates suggested the jet extended roughly 6,200 miles, or about 10,000 kilometers from the nucleus surface. That's a substantial feature, visible in multiple images taken days apart. The persistence of the jet indicated sustained activity rather than a brief outburst. Something about 3I Atlas's rotation period or surface properties was keeping this active region pointed roughly toward the Sun for an extended time. Models would later propose that carbon dioxide sublimation was ejecting water ice fragments along with dust, and these ice fragments efficiently scattered sunlight, creating the visible jet. Carbon dioxide ice sublimates at lower temperatures than water ice, so it can drive activity further from the Sun. When carbon dioxide gas expands rapidly, it can entrain chunks of water ice that would otherwise remain frozen. This mechanism has been observed in solar system comets, particularly those with high carbon dioxide content. Comet Hale-Bopp in 1997 showed strong carbon dioxide activity driving dust emission. More recently, several comets observed by ground-based telescopes and spacecraft have exhibited similar behavior. So the mechanism isn't exotic, but seeing it in an interstellar comet reinforced the idea that 3I Atlas has unusually high carbon dioxide abundance. But in early August, the jet was just another piece of a very strange puzzle. The discovery helped explain the antitail, providing a physical mechanism for material streaming toward the Sun. But it deepened the mystery of what was causing such focused activity. Was it the nucleus rotation? Surface composition? Internal structure? Something about the way 3I Atlas formed or evolved in interstellar space? September brought observations from the Nordic Optical Telescope, another 2.5-meter instrument in the Canary Islands. These images, captured throughout September, documented a transformation that nobody had quite expected. The antitail that had been pointing toward the Sun started to weaken. Meanwhile, a regular tail pointing away from the Sun began to grow. By late September, the antitail had essentially disappeared, replaced by a conventional dust tail streaming behind the comet as it raced toward perihelion. David Jewett and Jane Liu, the astronomers analyzing the Nordic data, noted that the mass loss rate scaled roughly with the solar radiation flux hitting the surface. This square law relationship, flux proportional to inverse square of distance, is consistent with carbon dioxide being the main driver of activity. As the comet got closer to the Sun, solar heating intensified, sublimation rates increased, and more material was ejected. The sunward jet apparently shut off or redirected as the nucleus rotation changed the orientation of the active region. Meanwhile, enhanced outgassing on the sun-facing hemisphere created enough pressure to push a proper tail outward. The transformation from antitail to tail happened over the course of weeks, captured in image sequences that showed the evolution in near real time. This kind of morphological evolution is actually quite common in comets, though it's rarely observed in such detail for an interstellar visitor. Many comets develop complex tail structures that change as the comet moves along its orbit and as the nucleus rotates. What appeared to be a sunward jet at one viewing geometry might become a conventional tail when seen from a different angle, or after the nucleus has rotated. The key insight from the Nordic observations was that 3I Atlas was behaving dynamically. It wasn't a static object, but an active, evolving system, responding to changing solar illumination and internal processes. This dynamic behavior suggested the nucleus was rotating, that different regions had different compositions or activity levels, and that the comet's appearance would continue changing as it approached perihelion. The measured rotation period was uncertain, but estimates suggested something on the order of hours to days. Fast enough that different regions would rotate into sunlight on timescales we could observe, but slow enough that individual active regions could remain illuminated long enough to produce sustained jets. This is typical for comet nuclei, which have rotation periods ranging from a few hours to several days, depending on their size, shape, and formation history. This is where the story takes a turn into territory that's harder to observe from Earth. As 3I Atlas continued its inward journey, it made its closest approach to Mars at about 30 million kilometers. This might seem like a huge distance, and it is by everyday standards, but in astronomical terms, it represented a rare opportunity. Spacecraft orbiting Mars could potentially observe this interstellar visitor from a completely different perspective than Earth-based telescopes. The European Space Agency had two orbiters in position, ExoMars Trace Gas Orbiter and Mars Express. NASA had its own fleet, including Mars Reconnaissance Orbiter with its powerful HiRISE camera, and several other spacecraft capable of imaging or spectroscopy. Between early and mid-autumn, these spacecraft turned away from their usual observations of the Martian surface to hunt for 3I Atlas. Spacecraft observations from Mars offered several advantages. First, a different viewing geometry. From Mars, the comet would be seen from a different angle than from Earth, potentially revealing structure invisible from our perspective. Second, simultaneous observations from two planets would allow parallax measurements that could help constrain distance and size. Third, some spacecraft instruments operate at wavelengths inaccessible from Earth's surface due to atmospheric absorption. The ExoMars Trace Gas Orbiter succeeded spectacularly using its color and stereo surface imaging system called CASIS. This camera was designed to image the Martian surface at high resolution, studying geology, erosion, and potential landing sites. But it's a versatile instrument, and with careful planning, it could be pointed at targets beyond Mars. The orbiter captured a series of images with 5-second exposures. In those images, 3I Atlas appears as a slightly fuzzy dot moving through the frame as the spacecraft tracked the starfield. Background stars are streaked into lines because the camera was staring at a fixed point in space, letting the comet drift through the view. This technique is the opposite of what you'd do to track the comet itself, but it allowed CASIS to maintain stable pointing while the comet moved relative to background stars. The dot represents the nucleus and its surrounding coma, the inner part of the gas and dust cloud that's bright enough to register on a camera designed for photographing Mars. CASIS could not distinguish the nucleus from the coma because 3I Atlas was still 30 million kilometers away. At that distance, resolving a kilometer-sized nucleus would require angular resolution far beyond what any Mars orbiter possesses. Think about the geometry. A 1-kilometer object at 30 million kilometers subtends an angle of about 0.007 arcseconds. That's incredibly tiny, well below the diffraction limit of any spacecraft camera. The Hubble Space Telescope, with its 2.4-meter mirror, has a diffraction-limited resolution of about 0.05 arcseconds at visible wavelengths. CASIS, with its much smaller optics, couldn't possibly resolve something that small. But the Coma, measuring a few thousand kilometers across, was clearly visible. The images showed that the bright glow around 3I Atlas extended to roughly 680 kilometers from the nucleus, at least the part bright enough for CASIS to detect. The surface brightness falls off rapidly with distance, following an inverse square or steeper law, fading into noise beyond a certain radius. So the full extent of the Coma was certainly larger than what appeared in the images. Nick Thomas, principal investigator for CASIS, called it a very challenging observation. The comet was tens of thousands of times fainter than the spacecraft's usual target. CASIS is optimized for imaging the brightly lit Martian surface, just hundreds to thousands of kilometers below. The camera settings, exposure times, and data processing are all tuned for that specific observing scenario. Pointing it at a dim, fuzzy object 30 million kilometers away pushed the instrument to its absolute limits. Exposure times had to be maximized to collect enough photons. Pointing had to be extraordinarily precise to keep the target in the field of view despite spacecraft motion. Post-processing had to extract weak signal from noise. But it worked, delivering images that provided a unique perspective on the comet's coma structure. Still, this was a sideways view, perpendicular to the line from the comet to the sun. From this angle, observers could see the structure of the coma in profile, rather than face-on. If the coma had any asymmetry or directional features, they would be more apparent in profile view. The images hinted at possible structure, but nothing definitive at the available resolution. Mars Express, meanwhile, struggled to capture 3I Atlas. The high-resolution stereo camera aboard Mars Express had a maximum exposure time of just 0.5 seconds, compared to Cassis's 5 seconds. That tenfold difference in light gathering capability proved critical. When imaging a faint comet, more exposure time means more photons collected, and that translates directly to signal-to-noise ratio. 3i Atlas has not yet revealed itself clearly in Mars Express images, though scientists are attempting to stack multiple exposures together to boost the signal. This technique, called co-adding or stacking, is standard in astronomy. By aligning multiple images on the target and averaging them, random noise decreases while the signal adds coherently. If you stack 10 images, the noise decreases by a factor of square root of 10, while the signal increases linearly, improving signal-to-noise by that factor. Whether stacking will successfully extract 3i Atlas from Mars Express data remains to be seen. The spacecraft also attempted spectroscopy using its Omega and SpyCam instruments, trying to measure the composition of the gas cloud. But whether the comet was bright enough for full spectral characterization is uncertain. Spectroscopy typically requires more photons than imaging, because you're spreading the light across many wavelength bends. The most anticipated images were supposed to come from NASA's Mars Reconnaissance Orbiter. The HiRISE camera aboard MRO is the highest resolution camera we've ever sent to another planet. It was designed to image features as small as 30 centimeters across on the Martian surface, looking for suitable landing sites and studying geological features in extraordinary detail. Pointed at 3i Atlas from a distance of 30 million kilometers, HiRISE would have a spatial resolution of about 30 kilometers per pixel. That might not sound impressive compared to its centimeter-scale resolution on Mars, but it's roughly 3 times better than the best Earth-based images at the time. At that resolution, the brightest pixel in the image would provide an excellent constraint on the actual surface area of the nucleus. If the nucleus was several kilometers across, it would span multiple pixels, allowing measurements of its shape and orientation. If it was at the smaller end of estimates, just hundreds of meters across, it might appear as a single bright pixel, surrounded by fuzz from the Coma. Either way, HiRISE could finally nail down whether we're looking at a half-kilometer rock or a 5-kilometer giant. HiRISE almost certainly observed 3i Atlas during the Mars flyby window. The observation would have been a high priority for the science team, and MRO had the fuel and pointing capability to execute it. But those images haven't been publicly released. The US government experienced a shutdown in early October, furloughing thousands of NASA workers and halting public communications and data releases. As of late October, the HiRISE data remains locked away somewhere in NASA's archives, waiting for the shutdown to end and staff to return. Scientists are eager for it. The public is curious about it. But bureaucracy has its own timeline, and 3i Atlas doesn't wait for anyone. Eventually, the images will be released, and they'll either confirm size estimates or force revisions. This situation illustrates one of the frustrations of modern astronomy. We have incredible instruments, capable of extraordinary observations, but their data doesn't always reach the public, or even the scientific community, on timescales matched to public interest. Papers take months to write and clear peer review. Data archives require careful calibration and documentation before release. Administrative processes add further delays. For a dynamic, time-sensitive target like 3i Atlas, these delays are frustrating. The comet is active, changing, evolving. Real-time or near real-time observations provide context that's lost if data sits in archives for months. But the system we have balances immediate communication with careful validation, and sometimes validation takes time. While the professional observatories were gathering data from their massive instruments, amateur astronomers around the world were also tracking the comet with their own equipment. The democratization of astronomy in recent decades has been remarkable. What once required million-dollar facilities can now be accomplished with thousands of dollars worth of telescope, camera, and computer. The Unistellar Smart Telescope Network represents this new generation of citizen science.
Unistellar telescopes are AI-powered instruments that automatically point themselves at targets, track them as they move across the sky, stack multiple exposures in real time, and display enhanced images that make faint objects visible to equipment that would have been considered amateur-grade just years ago. The system uses sophisticated image processing algorithms running on embedded computers to extract weak signals from background noise. Community members like Bruno, Scott Cardell, and Frank Marsh contributed observations of 3I Atlas throughout summer. Their images captured the comet at magnitude 17 to 19, far too faint for visual observation through any telescope, but accessible to modern CCD and CMOS cameras with sufficient exposure time. These observations help track the comet's brightness and position, supplementing professional data and filling gaps when major observatories were pointed elsewhere. This kind of distributed observing network has become invaluable for monitoring transient phenomena. Supernovae, variable stars, asteroid occultations, comet outbursts, all benefit from having many eyes watching from different locations. Professional astronomers can't observe everything all the time. Amateurs provide coverage that would be impossible to achieve with major facilities alone. But not all amateur observations went smoothly, and herein lies a cautionary tale about modern astronomy in the social media age. Around the time of the Mars flyby, coinciding precisely with maximum public interest, a heavily processed image went viral across multiple platforms. The image, captured using Dobsonian telescope equipment with solar filters, showed what appeared to be unusual structure in 3I Atlas. The timing was suspicious. The image quality raised immediate red flags among professionals. Solar telescopes use specialized filters designed for observing the blindingly bright sun, not faint deep space objects. These filters block most wavelengths, transmitting only narrow bands suitable for solar observation. Using them for comets makes no sense optically and suggests either misunderstanding of equipment or deliberate manipulation. Dobsonian mounts, while excellent for visual astronomy and providing stable platforms for large aperture telescopes at reasonable cost, lack the precise tracking needed for long exposure imaging of fast-moving comets. They're alt-azimuth mounts, not equatorial, which means they can't compensate for Earth's rotation with a single motor. For deep sky astrophotography, you need equatorial mounts that track the sky's rotation. The viral image was almost certainly a composite of many frames stacked together using aggressive processing. And here's where things get tricky. When you stack multiple images, you're adding signal but also adding noise. If you then apply heavy contrast enhancement, histogram stretching, or sharpening filters, you amplify both signal and noise. Noise can look like structure if you want it to badly enough, especially if you're primed to see certain features. The professional community quickly analyzed the image and pointed out the issues. The structures people were seeing appeared to be artifacts of processing, atmospheric turbulence, and optical aberrations. But not before conspiracy theories spread across the internet, particularly Russian language sites, where speculation about 3I Atlas being an artificial object had gained traction. This incident illustrates one of the challenges of modern astronomy communication. In the age of digital image processing and social media, anyone can create something that looks impressive. Images can be manipulated, enhanced, and selectively presented. Without understanding the technical details, exposure times, equipment specifications, processing methods, it's difficult for the public to distinguish genuine data from artifacts. Scientists face a dilemma. If they remain silent, misinformation spreads unchecked. If they respond, they risk amplifying the false claims by drawing more attention to them. The solution, imperfect as it is, involves patient explanation of how observations work, what constitutes reliable data, and why certain claims don't hold up under scrutiny. It's slow, unglamorous work, but necessary. A more credible amateur contribution came from astrophotographer Simeon Schmaus, who carefully stacked 20 images from the Mastcam camera aboard NASA's Perseverance rover on Mars. In that stack, Schmaus found a faint smudge of light in the constellation Corona Borealis.
close to where 3i Atlas was expected to appear in the Martian sky during early autumn. If confirmed, this would be the first detection of 3i Atlas from the surface of another planet. But confirmation is tricky, and this is where professional analysis becomes crucial. The smudge is very faint, barely above the noise level in stacked images. Other candidates exist for what it might be: background galaxies, cosmic ray hits on the detector, image processing artifacts. All can produce faint smudges that resemble distant objects. Without careful calibration and analysis, it's impossible to say with certainty whether the smudge is 3i Atlas or something else. NASA's official analysis, which would provide definitive answers, has been delayed by administrative issues. The rover team has the data. They've presumably analyzed it, but public release awaits bureaucratic processes. This is another example of how institutional timelines don't always match public curiosity. Eventually, we'll know whether Perseverance successfully imaged the interstellar visitor. For now, it remains uncertain. Another image from Perseverance's right navigation camera generated even more attention. The image showed a streak of light in the Martian sky captured during evening local time. The streak appeared cylindrical and elongated, and social media users immediately declared it evidence that 3i Atlas is not a comet, but something artificial. The speculation reached fever pitch on Russian-language forums and news sites. Avi Loeb, the Harvard astrophysicist who has been publicly vocal about the possibility of interstellar objects being technological in nature, analyzed the image and provided a measured explanation. The cylindrical appearance, he noted, is an artifact of image stacking and motion. It's not what 3i Atlas actually looks like. The navigation camera has angular resolution of about 0.33 milliradians, which translates to roughly 68 arcseconds per pixel. At 3i Atlas's distance of 38 million kilometers during the Mars encounter, that corresponds to approximately 12,500 kilometers per pixel. The actual nucleus of 3i Atlas is at most a few kilometers across, far smaller than a pixel. So what we're seeing in any single image is just the Coma and tail smeared across multiple pixels. The streak in the viral image spans about 4 pixels, making it roughly 50,000 kilometers long in the image. But this doesn't mean the comet is 50,000 kilometers long. It means the comet moved 50,000 kilometers during the image acquisition sequence. The navigation cameras on Perseverance take many short exposures over time to build up signal. When you stack those exposures while tracking the star field, anything moving gets smeared into a trail. It's exactly the same effect that creates star trails in long exposure photography when you don't track the stars. Each individual snapshot shows a circular point. But when you combine many snapshots taken over time while keeping the camera fixed, stars become streaks. The comet moved, the camera tracked the background sky, and the result was a streak. Not a spacecraft, just image processing, revealing the motion of a natural object. Loeb's analysis was careful and scientifically sound, explaining the image in terms of known processes. But his involvement added fuel to speculation because of his public position on technological explanations for anomalous objects. Loeb has argued that we should seriously consider the possibility that some interstellar visitors might be artificial, that the anomalous acceleration of Oumuamua deserved technological explanations alongside natural ones. This position is controversial within astronomy. Most scientists believe Oumuamua's acceleration is explained by outgassing, even if we can't see the Coma directly. They argue that invoking artificial origin without strong evidence violates Occam's razor and scientific conservatism. Loeb counters that scientific conservatism shouldn't prevent us from considering all possibilities, especially when natural explanations have problems of their own. The debate is healthy in principle. Science advances by considering alternatives and testing them against data. But in practice, the public discussion often becomes polarized. Those who favor natural explanations accuse Loeb of sensationalism.
Those who find technological hypotheses intriguing accuse mainstream astronomers of close-mindedness. The truth probably lies somewhere between, as it usually does. 3i Atlas, for its part, has shown no clear evidence of artificial origin. Its composition, activity, and behavior are all consistent with a natural comet, albeit one with unusual chemistry.
The carbon dioxide dominance, the nickel without iron, the anti-tail, all these can be explained by natural processes, even if some details remain uncertain. Nothing requires invoking technology. But Loeb and others point out that absence of evidence for artificial origin isn't evidence of absence. Just because we can explain observations with natural processes doesn't mean that's definitely what we're seeing. This is philosophically true, but practically difficult to work with. If every unexplained detail is potentially evidence of technology, where do you draw the line? The scientific community's answer is, extraordinary claims require extraordinary evidence. If you want to claim an object is artificial, you need to show something that natural processes can't explain. Anomalous acceleration might count if you can definitively rule out outgassing. Radio transmissions would certainly count. Regular geometric structures might count, but unusual chemistry or activity patterns that fit within the bounds of known physics don't meet that bar. Even as amateur and professional observations accumulated, one more eye was watching from space. NOAA's GOES-19 satellite, positioned in geostationary orbit to monitor Earth's weather, carries an instrument called Core 1, a coronagraph designed to block out the sun's overwhelming glare so that the faint corona and nearby objects become visible. Coronagraphs are essential tools for studying the sun's outer atmosphere and for detecting comets that pass very close to the sun. In late October, as 3i Atlas passed behind the sun from Earth's perspective, citizen scientist Warichet Boonplod discovered the comet in Core 1 images. This was a significant find because for a brief window, this coronagraph was the only instrument on Earth or in near-Earth space capable of observing 3i Atlas. The comet appeared as a faint dot moving through the field of view, heading toward perihelion. Solar conjunction, the moment when an object appears directly behind the sun from our perspective, is a challenging time for observations. The sun's glare overwhelms faint objects nearby. Ground-based telescopes can't observe within a certain angular distance of the sun because pointing too close risks damage to instruments and provides no useful data anyway. Space telescopes face similar constraints, unless specifically designed for solar observation. But coronagraphs solve this problem by using an occulting disk to block the sun's photosphere while allowing observation of the surrounding corona and background space. SOHO, the Solar and Heliospheric Observatory, has discovered thousands of comets using this technique. Most of them sun-grazing comets that pass extremely close to the sun and usually don't survive the encounter. 3i Atlas wasn't a sun-grazer. Its perihelion distance of 1.36 AU placed it well outside any danger zone. But from Earth's perspective, it passed through the coronagraph field of view, and that allowed continued tracking through the critical perihelion phase. These observations filled a gap that would otherwise have existed in the observational record. Perihelion occurred around October 29th, when 3i Atlas reached its closest point to the sun at approximately 130 million miles, just inside the orbit of Mars. At that distance, solar radiation delivers enormous energy to any object. The solar constant at Earth's orbit is about 1,361 watts per square meter. At 1.36 AU, it's reduced by the inverse square of distance, giving roughly 730 watts per square meter. For a nucleus several kilometers across, the total power input is measured in gigawatts. Imagine tens or hundreds of nuclear power plants worth of energy slamming into a ball of ice and rock. That energy heats the surface, drives sublimation, creates pressure that fractures the crust, and can even cause catastrophic fragmentation if the nucleus is structurally weak. Many comets undergo outbursts or fragmentation near perihelion. Thermal stress creates cracks. Pressure from subsurface gas builds until something gives way. If the nucleus has internal voids or weak zones, it can split apart into multiple fragments, each following slightly different orbits. Comet Shoemaker-Levy 9, famous for impacting Jupiter in 1994, broke apart during a close pass of Jupiter, torn apart by tidal forces. 3I Atlas faced no such tidal threat. Jupiter was far away, and gravitational forces were minimal. But thermal stress at perihelion was significant. Whether the nucleus could survive intact depended on its internal structure and strength. Was it a monolithic chunk of ice and rock, or a loosely bound pile of rubble? Did it have internal voids, or was it relatively homogeneous? These questions couldn't be answered directly, but would be revealed by post-perihelion observations. If the comet emerged intact, continuing to show normal activity levels and a single bright nucleus, it would suggest structural integrity. If it fragmented, we'd see multiple pieces, each with its own coma, spread along the orbital path. If it underwent a major outburst, brightness would spike dramatically, as buried ices suddenly exposed to sunlight rapidly sublimated. We couldn't see perihelion directly. The sun blocked our view, but the coronagraph images provided some constraints, showing that the comet was still active and intact as it approached closest solar distance. The real test would come in November, when 3I Atlas emerged from behind the sun and became observable again from Earth. Every telescope that observed 3I Atlas revealed something new, something unexpected, something that didn't quite fit comfortable models. The anti-tail that transformed into a regular tail, the carbon dioxide dominance where water should prevail, the nickel without iron, the sheer size uncertainty, with estimates ranging from hundreds of meters to tens of kilometers. Each wavelength, each instrument, each perspective added pieces to a puzzle that wasn't coming together into a simple, coherent picture. Instead, the picture fragmented further with every observation. 3I Atlas wasn't just unusual for an interstellar object, it was unusual compared to anything astronomers routinely study. And as of late October, the comet has passed behind the sun, reaching solar conjunction when it appeared exactly opposite Earth. Days later, it arrived at perihelion, bathed in intense solar radiation that we could only imagine from our distant, blocked viewpoint. We're in the dark. Literally. The comet is behind the sun, experiencing whatever perihelion does to an object of its composition and structure. And we can only wait and wonder. November will bring answers. The European Space Agency's Jupiter Icy Moons Explorer, JUICE spacecraft, will fly within 64 million kilometers, offering the first post-perihelion data with its sophisticated instruments. JUICE was launched in 2023 on a long journey to Jupiter, but its trajectory takes it through the inner solar system multiple times for gravity assists. One of those passages happens to coincide with 3I Atlas emerging from behind the sun. The spacecraft wasn't designed to observe comets, but mission planners recognized an opportunity. With careful scheduling, JUICE can point its cameras and spectrometers at the comet, capturing data that complements Earth-based observations. Ground-based telescopes will pick up the comet around mid-November once it emerges from the sun's glare. By then, it will be moving outward, receding from the sun and gradually dimming as solar heating decreases. The critical question is what condition it's in. Intact or fragmented? More active or less? Brighter or fainter than predictions based on pre-perihelion behavior? These observations will reveal perihelion's effects. By late December, 3I Atlas will make its closest approach to Earth at 168 million miles, about 1.8 astronomical units. That's still an enormous distance, more than twice the Earth-Mars separation when Mars is at opposition. Far too distant to pose any threat, but close enough for detailed spectroscopy and high-resolution imaging from the best ground-based telescopes and space observatories. This will be the optimal viewing window from Earth. The comet will be relatively close, positioned for nighttime observations, and hopefully still active enough to be scientifically interesting. Observing campaigns are being planned. Telescope time is being requested. Instruments are being prepared. The astronomical community is ready to capture as much data as possible during this window. And then, in March 2026, as the comet speeds outward past Jupiter's orbit, NASA's Juno spacecraft will observe it from approximately 54 million kilometers away. Juno, currently orbiting Jupiter on its extended mission to study the giant planet's atmosphere, magnetosphere, and moons, will have one brief opportunity to point its instruments at the departing visitor. This will be the last high-quality observation before 3i Atlas leaves the inner solar system forever. Juno's instruments include visible and infrared cameras, a radio and plasma wave instrument, and magnetometers. While not optimized for comet observation, they can provide valuable data on the comet's continued activity, composition, and interaction with the solar wind at large heliocentric distances. After that, 3i Atlas will fade from view, moving outward through the asteroid belt, past the giant planets, toward the heliopause where the sun's influence ends and interstellar space begins. Years from now, decades from now, it will be gone, traveling through the darkness between stars once again. Its brief passage through our solar system will be complete, leaving behind only the data we managed to collect and the questions that data raised. But for now, in late October 2025, we're at a crucial moment. The comet is behind the sun, experiencing maximum solar heating, and we're waiting to see what happens next. Every image captured so far has told us that 3i Atlas doesn't behave exactly as expected. The question is whether post-perihelion observations will resolve the mysteries or deepen them further. Based on the pattern so far, each new observation revealing something unexpected, deeper mysteries seem more likely than simple answers. This is a comet that has consistently refused to fit comfortable categories. It's not like Oumuamua, that strange tumbling cigar shape with unexplained acceleration. It's not like Borisov, reassuringly normal in most respects. It occupies its own category, exhibiting both familiar and unfamiliar properties in combinations we haven't seen before. Think about what we've documented. We've turned the most powerful instruments humanity has ever built toward this object. The Hubble Space Telescope, with its 3 decades of discoveries. The James Webb Space Telescope, representing the cutting edge of infrared astronomy. Keck and Gemini and the Very Large Telescope, ground-based giants that push the limits of what's observable from Earth's surface. Spacecraft orbiting Mars, capturing unique perspectives, all focused on one target. And instead of converging on a clear understanding, the data fragments into complexity. More observations haven't meant simpler answers. They've meant more questions, more anomalies to explain, more details that don't quite fit standard models. That's not how science usually works. Usually, initial observations raise questions, but additional data resolves them. More measurements reduce uncertainty. Better instruments provide clarity. But 3i Atlas seems to operate by different rules. Every answer raises 2 new questions. Every solution reveals a deeper problem. The images we have are extraordinary. Teardrop comas in Hubble's sharp view. Sunward jets captured by ground-based telescopes. Carbon dioxide plumes extending hundreds of thousands of kilometers, mapped by SPHEREx. Nickel emissions without accompanying iron, detected by Keck spectrographs. A tail that points the wrong direction and then transforms into a conventional tail as we watch. Fuzzy dots captured from Mars orbit, showing the comet from a sideways angle. Streaks across the Martian sky. Artifacts of motion revealing how fast this visitor travels. Coronagraph glimpses as the comet vanishes behind our sun,
continuing its journey through the most intense radiation it will experience during its solar system passage. Each image is a snapshot of something that challenges our expectations. Each piece of data tells us 3I Atlas came from somewhere else, somewhere with different formation conditions, different chemistry, perhaps different processes operating in protoplanetary disks around other stars.
It traveled for potentially millions of years through the darkness between stars, cold and inactive, accumulating cosmic ray exposure, occasionally passing through molecular clouds, experiencing the galactic environment in ways we can only imagine. And now, it's here, briefly illuminated by our sun, revealing chemistry and structure that expand our understanding of what's possible. Carbon dioxide, where we expected water, suggesting formation in regions of its home protoplanetary disk, where temperature and pressure conditions favored carbon dioxide ice over water ice. Nickel without iron, hinting at exotic chemical processes we associate with industrial laboratories, but apparently occurring naturally in this strange visitor. Jets pointing toward the sun instead of away, driven by asymmetric outgassing that reflects the nucleus's rotation and surface properties. A transformation from anti-tail to regular tail as activity patterns changed with heliocentric distance and illumination geometry. Every observation adds depth to the mystery rather than resolving it into simplicity. The scientific community is doing what it does best: observing, measuring, analyzing, hypothesizing, debating, refining models. Papers are being written, submitted to journals, subjected to peer review. Data is being shared through professional channels, and increasingly through public archives. Models of cometary composition and activity are being updated to account for what we're seeing. The process is methodical, careful, and slow by the standards of internet speed information flow, but underneath that methodical approach, there's genuine excitement mixed with bewilderment. 3I Atlas is strange enough to be genuinely interesting, unusual enough that it teaches us something new, but not so bizarre that it breaks our understanding entirely. It exists in that sweet spot where science happens most productively, challenging assumptions while remaining explicable within known physics. When Oumuamua passed through, it forced reconsideration of what interstellar objects could look like. Its elongated shape, inferred from brightness variations, suggested axis ratios unprecedented for natural objects. Its unexplained acceleration challenged standard comet models, leading to proposals ranging from hydrogen icebergs to light sails. It expanded the parameter space of possibility, showing that interstellar visitors might be fundamentally different from solar system natives. When Borisov arrived 2 years later, it was reassuring in its relative normalcy. Here was a comet that looks like a comet, with a bright coma and tail, releasing water vapor and carbon monoxide, behaving according to established models. Yes, it had peculiarities, unusual carbon monoxide abundance, different dust properties, but nothing that broke existing frameworks. It showed that interstellar comets could be comprehensible. 3I Atlas occupies middle ground between these extremes. It's comet-like in many respects, with coma, tail, outgassing, dust emission, all the features we expect. But its composition pushes boundaries. 87% carbon dioxide is far beyond anything seen in solar system comets. The nickel to iron ratio is orders of magnitude different from expected values. These aren't minor variations. They're fundamental differences that speak to distinct formation conditions. The carbon dioxide dominance is perhaps the most significant finding. It tells us directly that planetary systems around other stars can produce objects with chemical compositions dramatically different from ours. Water is abundant throughout the universe. It's one of the most common molecules formed from the most common elements.
but carbon dioxide abundance depends on carbon to oxygen ratios, temperature structures in protoplanetary disks, and formation timelines. A system with elevated carbon to oxygen ratio, perhaps formed from molecular cloud material enriched in carbon from previous generations of stars, might produce carbon dioxide-rich comets. A disk with unusual temperature gradients might have a carbon dioxide ice line farther from the star than typical, creating a larger zone where carbon dioxide dominates over water. These are testable ideas that can be explored through models and observations of other planetary systems.
The nickel without ion finding is equally intriguing, but more difficult to explain definitively. The speculation about nickel tetracarbonyl chemistry is based on sound reasoning. It's a known process that selectively volatilizes nickel. But invoking it for a natural comet requires explaining how the necessary conditions arise. Do you need a carbon monoxide-rich environment? Specific temperatures? Catalytic surfaces? Or is there an entirely different explanation involving unusual nucleus composition? These questions drive current research. Spectroscopists are analyzing data in detail, looking for additional chemical signatures that might constrain models. Theorists are running simulations of protoplanetary disk chemistry, exploring what conditions produce carbon dioxide-rich objects. Dynamicists are calculating ejection mechanisms, trying to understand how objects leave their birth systems and become interstellar wanderers. All of this work takes time, and the payoff might not come for years. But that's how science operates. Observations raise questions. Questions inspire research. Research produces models. Models make predictions. Future observations test predictions. The cycle continues, each iteration refining our understanding incrementally. Progress is rarely dramatic, but it's cumulative. What we learn from 3i Atlas will inform interpretation of future interstellar visitors. And there will be future visitors. 3i Atlas is only the third confirmed interstellar object, but estimates based on detection statistics suggest these objects pass through the inner solar system regularly. We're only now reaching the point where our surveys are sensitive enough and wide enough to catch them reliably. The Vera Rubin Observatory, which began operations recently, will dramatically increase detection rates. Within a decade, we might have dozens of interstellar objects to study. Each will provide a sample from another planetary system, delivered to our doorstep without need for interstellar spacecraft. Each will teach us about the diversity of planetary formation conditions across the galaxy. Each will refine our statistical understanding of what's common and what's rare. This is comparative planetology on a galactic scale, made possible by objects that happen to wander through our neighborhood. The visual legacy of 3i Atlas is already secure. Images captured by the world's premier observatories will be studied for years, providing reference data for models and comparisons with future objects. They document in unprecedented detail what an interstellar comet looks like as it passes through the inner solar system, how it responds to solar heating, how its activity and appearance change with time and viewing geometry. Future researchers will return to these images, finding details we missed, applying new analysis techniques, testing new hypotheses. The Hubble images of the antitail, the Webb spectra showing carbon dioxide dominance, the Keck detections of nickel, the Mars orbiter observations, all will become part of the permanent scientific record, available to anyone who wants to understand interstellar visitors. And somewhere out there, in the vast space between stars, other objects continue their journeys. Some will eventually pass through our solar system, giving us new opportunities to observe, measure, and learn. With each new detection, our sample size grows. With each new dataset, our understanding deepens. 3i Atlas is one chapter in a much longer story, the story of how material moves through the galaxy and what that material teaches us about the cosmic environment we inhabit. For now, we wait. Wait for November, when the comet re-emerges from behind the sun. Wait for new images, showing how it survived perihelion. Wait for spectra, revealing whether composition or activity changed. Wait to see if 3i Atlas has any final surprises in store for us. Based on everything we've observed so far,
assuming we've seen all this object has to offer would be premature.
The most interesting discoveries in astronomy often come when we least expect them, from observations that reveal something nobody predicted. You point your instruments at the sky, collect data carefully, analyze it rigorously, and sometimes the universe shows you something that doesn't make immediate sense. Something that challenges your understanding and forces you to think differently. 3i Atlas has been exactly that kind of object from the beginning, and there's no compelling reason to believe it's finished teaching us. The countdown continues as we approach late November 2025. The comet continues its outward journey, gradually receding from the sun, beginning its long return to interstellar space. And we continue watching, instruments ready, minds open to whatever comes next. In a universe as vast and ancient as ours, there are always new mysteries waiting to be discovered. 3i Atlas is just one of them, but it's ours to study, our opportunity to learn, our window into the chemistry and physics of worlds beyond our solar system. That, ultimately, is what makes this pursuit worthwhile. Not because we expect answers to come easily or quickly, but because the questions themselves are profound and consequential. Where did this object form? And under what conditions? What can its unusual composition tell us about planetary systems around other stars? How common are carbon dioxide-rich comets in the galaxy? And what does their existence mean for our understanding of protoplanetary disk chemistry? How do objects become ejected from their birth systems to wander between stars? These questions are worth pursuing, even if answers take decades to fully emerge. The images and data will remain, permanent records of an interstellar visitor that passed through our neighborhood in 2025. Future generations of astronomers will look back at these observations as foundational work, early steps in humanity's effort to understand the broader galactic environment. They'll see what we saw, a comet that challenged expectations, that revealed chemistry both familiar and strange, that expanded the catalog of what's possible in the universe. Perhaps they'll have answers we don't yet possess. Perhaps with more sensitive instruments, larger datasets from dozens of interstellar visitors, and refined theoretical models, the mysteries of 3i Atlas will resolve into clarity. Or perhaps this comet will remain one of those objects that never quite fits perfectly, a reminder that nature is under no obligation to conform to our categories, and that surprises await those patient enough to watch the sky. The beauty of astronomy lies in this ongoing dialogue between observation and theory, between what we expect and what we discover, between comfortable models and uncomfortable data. 3i Atlas has given us uncomfortable data, carbon dioxide where water should dominate, nickel without iron, antitails that transform into regular tails. Each piece challenges some aspect of our understanding, forcing refinement and expansion of models. And that's how science advances. Not through simple confirmation of what we already believe, but through challenges that force us to think more deeply, consider alternatives, refine theories, and ultimately emerge with better understanding. 3. Atlas, with all its peculiarities and mysteries, is a gift to science. A natural experiment designed by the universe, delivered to us across light years of space, asking us to figure out its secrets. As we conclude this story, though the Comet story continues, reflect on what we've learned and what remains unknown. We've documented the third confirmed interstellar visitor to our solar system. We've measured its composition and found it dramatically different from expectations. We've watched its activity evolve as it approached the sun. We've captured images from multiple planets and spacecraft. We've debated interpretations and refined models. And we've been reminded, once again, that the universe is stranger and more diverse than we imagine. The tale of 3i Atlas isn't finished. November and December will bring new chapters. Future papers will add analysis and interpretation. Other interstellar objects will arrive, providing comparison points. But this moment, late October 2025, represents a milestone. We've done everything current technology allows to characterize this visitor. We've gathered data that will fuel research for years. And we've added another entry to the shortlist of confirmed interstellar objects. Each one precious, each one irreplaceable. So watch the sky, follow the updates, read the papers. Think about what it means that objects from other star systems occasionally pass through ours, carrying information about distant worlds and ancient processes. Consider how fortunate we are to live in an era when detecting and studying these visitors is possible. And remember that somewhere out there, right now, other objects are making their slow journeys through interstellar space. Some will eventually reach our solar system. And when they do, we'll be ready.